Hello, my name is Luke Raymond. This is my lab 2 over projectile motion. Here's an overview of everything I'll talk about in my presentation. So the purpose of this lab is to measure a projectile's motion after it is tossed and compare measured data from tracker with two computational models, one accounting for drag force and one not accounting for drag force. And a preview of the result is that the computational model accounting for drag force will have a similar max height and be more similar to the observed motion than the model not accounting for drag force. So the three tools I used were Tracker, GlowScript, and Excel, and the main assumption I made is that the shape of the object does not affect airflow or resistance. For example, in this lab, I used a paper ball that was crumpled up, and I assumed that the crevices did not change the object's motion. The experimental procedure was to record an object in projectile motion, import the video to Tracker and track the ball's position frame by frame, create two computational models of the object's motion on GlowScript using initial values from Tracker. One of these models included drag force and one did not. And then I used Excel to create a y position versus time graph that contains the observed and predicted motions and compared both models to each other. So the fundamental physics principles were the momentum principle, gravitational force, and drag force. And the momentum principle tells us that the net force is only gravity and drag, so these are the only two forces acting on the object during its motion in the air. So using the momentum principle, we can drive the velocity update and position update formula, and each tell us that the only thing that changes the object's motion is the net force, so you can predict its velocity and position from that. And the system is the object being tossed, and the surroundings are everything else. Here's the Tracker model from the video analysis, and the max height was 0.436 meters, and the max distance traveled in the x direction was 0.991 meters, and here's the graph from that. So we use this data to get initial conditions and important quantities, and these are important because we will use them in our computational model to predict the object's motion over time. So here's the first computational model where Fnet is only gravity. So on the left, we plugged in all of the initial values and quantities, and then on the right, we ran a while loop to update the position's velocity, or the object's position and velocity over this time interval. And here the force net is only gravity, so it only accounted for that. And here's the graph that produced, where the max height was 0.441 meters, and the max range was 1.02 meters. So here's a computational model that accounts for drag force, and here I put all the initial values on the left, and on the right I ran the while loop to update the position's velocity, or the object's velocity and position over time. And here it accounted for drag force and gravity force. So here's the graph that produced, where the max height was lower than the one that did not account for drag, and the max height here was 0.436 meters, and the max range was 0.999 meters, or 0.995 meters. And here are the model comparisons with the Tracker model, computational model with drag, and the computational model without drag. And you can see that the computational model with drag is the most similar to the Tracker model of the observed motion, where they both reach the max height at about the same time. However, there's a little discrepancy between here and here about how fast the object came back down. So this could have been due to some errors, such as tracking errors or the shape of the object. So some tracking errors could have included misplacements or like when the tracking started. If I start the tracking after the ball's released, the initial velocity will be lower than like while the hand's still in contact with the object. So those could change up some things depending on when I start. And Tracker also could have glitched, as you saw the max height occurred at 2 points on Tracker that were right next to each other, so it could have messed up the step size. And then the other one was the shape of the object, which we technically assumed to ignore, but that could have changed while the computational model was different, because real life doesn't ignore this. So what does this mean with terminal velocity? And do either of our computational models predict terminal velocity? And no, neither of them did, because we would have seen the curve, or the velocity versus time graph, start to curve off at the bottom to level out at a specific velocity. That would have been known as the terminal velocity, and we don't see that here. But this is because the drag force was too low, so you couldn't really see the results or the effect. But here, if you were to make the drag force larger, which here I just threw in a number, made it larger so that we could see what it looks like, and you can see how the curve starts to level off around closer to zero-ish, like right in between 0 and 0.3, and that is how you predict the terminal velocity, because it shows you when drag force is equal to the force of gravity. And if the ball was thrown up with the same initial speed as the experiment, would this object take longer, shorter, or the same to reach the table height? And if the same initial speed was just the absolute value of uy, then it would be the same time. But if we're using speed, like literally, like the magnitude of the velocity, it would take longer. And here's all the math to prove it. And as you can see here, same as the computational model, and this is based on case 1, where this is the initial speed, just the magnitude of the y velocity only. And here, when you do the magnitude of like the velocity x and y, then you can see that will take a longer time than the computational model with no drag.